Hello, wonderful people of the internet. Welcome back to another episode of Simulaos. Today is an absolutely wonderful day. So, what are we doing today? Well, today we're going to be doing the introduction to GPU computing. Sorry about that. I had to write down a specific number. So, because I'm putting this on YouTube, I'm going to have to basically tell people the time at which the stream actually starts. So I have to know that number. It's a bit of a different game whenever I have to upload it to YouTube, but that's okay. What do we have here? As far as everyone coming in, I really appreciate it. QCD Quantum, Gathros, JSPP, what else do we have here? Baxas, everyone else, thank you guys so much for coming in. So today was a kind of requested episode. The way I see it is that someone basically asked, hey, could we do a intro to GPU computing on stream? And I was like, hey, you know, that's not a bad idea, but I don't know if I have time for it. Then I realized, hey, Gaussian elimination is going to be ending in, you know, a few days at that time. And so I figured, you know, how about we also just do the introduction to GPU computing at the end of this week, which is today, and it's Friday. So I didn't put much preparation into this. I know CUDA pretty well. I don't know OpenCL too incredibly well, but I know it well enough that I can usually get going with it. And also for the record, all of the code that we'll be doing and using is available just here at github.com/oist/GPU group. The stuff we'll be doing in particular will be under the Journal Club 1. Oh no, it'll actually be under the intro probably. And then we have CUDA, vectoradd.CUDA, and OpenCL, vectoradd.cpp. And that's basically how we do it. That's kind of what we're doing. I'm not going to use Vulkan. This is kind of a completely different game than what Vulkan, OpenGL, and DirectX, for example, can do. Like, this stuff has absolutely nothing to do with graphics. It has to do specifically with computation. So I figure, without further ado, we can just hop right into it. In the case that you guys want to talk about stuff, we can talk about it at the end of stream. Again, because this is going to be uploaded on YouTube, I kind of have to make sure that there's some, that we don't spend too much time rambling and stuff like that. Which I know, now you guys are going to say, just upload all videos to YouTube so you quit rambling. I understand. You can do computation with Vulkan. You are not incorrect. At this point in time, I think the OpenScale is going to be merged into... Thanks, JSPP, for fixing the algorithm command. So I think eventually OpenCL will be merged into Vulkan so it can do the computation here. But the thing is, Vulkan has a fundamentally different ideology. Like, it's meant to do something fundamentally different than OpenCL can do, or it was meant to do. And we'll talk about that. In fact, let's just go ahead and open up Zernal and let's give this guy a go. Okay. 1 second. Over here. And let me just go ahead and grab some stuff over here. Okay. So first of all, I've given this talk before. Like, I have, I've taught what's known as a skill pill at OIST on GPU computing. So this is a short, intensive course on some singular idea. The idea of the course for GPU computing was, of course, well, GPU computing. So we provided a series of problem sets for people to do. Also, I think available on the GPU group. You go under skill pill, you go to problems. We should have problem set.pdf. And let's see what we got here. I think this set of problems is just basic sets. So like we have vector addition and OpenCL. So in the, let's see, in the, what is it? The skill pill, we only really did CUDA. So if they wanted to check out OpenCL, they could do OpenCL. And I talked about why that would be important. Matrix transposition, this is actually a pain in the butt for a number of reasons. Not necessarily to do a basic transpose. Basic transposes can be done pretty straightforwardly. But to do the transposition efficiently with CUDA, it is a pain in the butt. An introduction to the cuFFT, because the cuFFT library was one of the libraries that people requested being able to use. Sobel filter, with or without an FFT. This is kind of, we had an example in there where we did a convolution. And the question was, hey, can you do the convolution with CUDA with or without the FFT? You know, there's two different ways to do it. I love my cow macro. That's amazing. Hey, Cobalt, thanks so much for coming in. And finally, parallel reduction, which is basically a method that allows you to do a parallel summation, like a summation of a vector in parallel, which is actually kind of crazy when you think about it, and we'll describe why that's crazy in a bit. So the problem set was actually really long. It took me a while to make. The vector addition in OpenCL, it's just, there's so much you have to talk about with OpenCL. It took like 4 pages. Matrix transposition, let's see, using QFFT. Subway filter, I didn't do too much about this one, and parallel reduction. I'm talking about these specifically because in the case that you guys wanted to you know, maybe look into this problem set later or do something with it, you could, you know, and so hopefully by the end of this discussion, you'll have enough information that you could, you know, potentially talk about this kind of stuff. So that's kind of where I was hoping to go by the end of today's session. Okay, so let's talk about it. GPU computing. What is the point? Why is it important? Why do people want to do GPU computing? What is the overall goal? Okay, well let's talk about it. So GPU computing. So, okay, I'm going to assume that because this is Twitch, or because this is going to be uploaded on YouTube, and my audience tends to be more of the programming-related audience or someone who does a lot of stuff on their computer, I'm going to assume that most people know what a GPU is, okay? But in the case you don't, a GPU is a device that's just like, you know, the card on your computer that displays graphics. It's the graphics processing, 1 second, unit. Now, again, I'm 90% sure everyone knows what this is. I just want to clarify in the case that people don't know. No, the graphics processing unit, which, by the way, is actually not graphical processing unit. It's actually graphics processing unit. I'm like 90% sure. It drives me nuts. I always get it wrong. Graphics processing unit. Yeah, it's not graphical, it's graphics. Yeah. Oh well, doesn't matter. Point is, I don't know why. I always think it's supposed to be graphical. Anyway, so the graphics processing unit, let's go, come on. I clearly don't know what I'm talking about, is a massively parallel device. So when I say parallel, I basically mean that the device itself can perform computation at the same time as other units in the computation. So this is distinctly different than a single CPU core. So for example, let's go new page before. In a CPU, we have basically, let's say, here is your amount of computation that you're allowed to do. 1, 2, 3. We'll say if you have an 8-core machine. Shoot, come on, let me try this again. We'll say if you have an 8-core machine. This means you can do basically 8 processes at the same time. And that's cool. Like, don't get me wrong, that's very, very useful. If it's hyper-threaded, this means you could potentially do up to 16, which basically means the cores can be used twice at the same time. Again, very cool. This level of parallelization is important because it means that we can run our code in parallel with different components at different points. The GPU, on the other hand, is a completely different beast. Rather than having only 8 cores, it has literally thousands of cores. Depending on your GPU, it could have more or less. So we'll say it has, I don't know, we'll just say 1,000 GPU cores. This is not standard for any GPU device to have 1,000. In fact, maybe 1,024 would be standard. But we'll just say 1,024 cores, okay? On the order of this. Now, that means that just by sheer magnitude, the GPU has way, way, way more cores available to it than the CPU. It has way more units of computation. However, each individual unit is much, much weaker, right? And this makes sense, right? Because the GPU has been optimized as a device to basically display, pixels on a screen. It should be able to upload or should be able to dynamically change, in this case, 1024 by, let's say, 1920 pixels, right? So that's 1,000,000 pixels in 60 frames per second. And that's a lot of computation to do, right? Like, we're talking about, again, 1,000,000 units of computation, 60 times a second. That's a lot. So in this way, the GPU has been optimized to just handle these small batch parallel processes quite quickly. Yep, exactly. So what Cobalt Ethan said is correct here. 1080 Ti has 3584 cores, 1070 has 1920. The number of cores here actually doesn't matter for a reason we'll talk about later. Let's see, graphical would be the GPU processing process information using graphics. So the units never met would be. Okay. So this is kind of why people want to use the GPU for computation, because again, the GPU has been optimized to do these incredibly small jobs, but do them all at once. Which means if you can take your problem and you can split it up into a parallel way, such that you can attack it all, like each individual component of the problem, you know, on its own, that's important. Because that means that now you can move your problem onto the GPU, and the GPU will almost undoubtedly give you a massive speed up in code. So this is what I mean. Let me just pop that over here. So let me show you an actual example here, and let me see if I can figure out where this is. I might not be able to find it. So it's probably in my GPU group somewhere. So let me just go to intro. I know it's probably under skill pill. Day one. Let's see, what do we have here? PNG, no, day1.tech, nice. I didn't even upload the freaking PDF, that's okay, it doesn't matter. What I'm gonna look for is GPUE. Nice, GPUE benchmarks at JPG, peterbritish.com. This is what I'm looking for. Okay, so in our particular code base, the one that we're using for, you know, everyday work, basically the idea, or a while ago, 2016, we had our code benchmarked versus basically other code in the area. So the Charter Suzuki MPI, GPUE, which is our code base, and GPE Lab, which is a CPU-based GPU or a CPU-based MATLAB implementation of our system. So GPUE right now is kind of it's way better than where it was back then, but that's okay. So what are we doing? We have the experiments, and then we have the actual results down here. Let's go ahead and view the image. Okay, so this is in logarithmic scale, okay? So this shows that, first of all, I mean, I don't mean to brag, but GPUE was faster than their Charter Suzuki code, like just in terms of benchmarks. That's pretty cool. Then, if we have a CPU-based implementation, even in a CPU-based implementation, we're like, you know, let's see, we're about 10 seconds to finish our computation. They're at about 50 to 60 seconds. So this means that we have a 5-time improvement, let's say, over the CPU-based code. And then on top of that, we have a literal 50 times improvement over MATLAB code for doing it this way. So basically, we took the MATLAB code. Oh, no, 500-time improvement here, it looks like. Anyway, we have a huge improvement over the MATLAB code. And this is well-optimized MATLAB code that people use for this very problem. So again, well-optimized MATLAB code, we're 50 times faster than that, and we're still 5 times faster than the well-optimized CPU-based code, which again is still done in parallel. So that is to say, if you do things on the GPU, you get a massive speed boost if you can do the computation on the GPU. So that's why people want to do the GPU computing, especially in scientific computing. You get a massive improvement in performance. So here are the actual units here. So real-time evolution 9, imaginary time evolution 19. These are just two different types of evolution. The GPE lab, which again is the MATLAB implementation, took 1859. So this is, oh wow, that's actually worse than I thought. This means that we are literally 200 times faster than the MATLAB implementation. Let's see, the CPU kernel, we're again 5 times faster than that. And not to brag, but we were pretty quick. So we were actually faster than the guy who was trying to benchmark their code. Let's see. So basically the point was that we have a massive improvement here by moving to the GPU, and that's why people want to do it. And that's, again, important because people care about computational time. I mean, you're talking about the area of high-performance computing where people will sit there and wait for literally months for their code to finish. You know what I mean? Like, you know, I don't know, they just sit there for months and, you know, sitting there, and then their code finishes, and they're like, great! GPU computing has the capability to take months down to days, or days, if your computation takes days, it has the capability to take that down to hours of time, and that's incredibly important. Now, obviously, if you're using MATLAB, you can get hundreds of times improvement over using lower level languages. In fact, you can get a 5 times improvement just moving down to using a lower level language like C++ or Fortran or something like that. But if you really want to get your bang, if you really want to get a fast computational method, then you want to do GPU computing. Now, as a note, GPU computing is way, way, way more complicated than standard CPU computing. So if you're going to do GPU computing, and you're going to use OpenCL and CUDA, which are the languages I'll be introducing now, expect a massive increase in development time. So even though the code runs 5 times quicker, the code takes 5 times longer to develop, oftentimes more than 5 times longer. So you have to kind of decide whether it's worth putting in the time to do the development, knowing that the code may only be run a few times, and so that depends. If you're developing software, it makes sense to do GPU computing. If you're developing just a quick scientific code base to use once or twice, then it's probably not worth it. I would be nervous all the time that there's a bug in my code. I'll be honest. I was incredibly nervous at this point last year because we had very few unit tests in our code. And what ended up happening, this is really dumb, but what ended up happening was I had a discussion with my boss where I basically just barely convinced him to let me put unit tests in the code, because like literally all I was doing was running the code for a day, coming back the next day, realizing there was a bug, fixing the bug, running it again, then realizing there was another bug, and then running it again, realizing there was another bug, and the code would take a day to run, sometimes a day and a half. So I'm sitting here just waiting for the code to run, come back in, and then I have to fix a bug. It was super not optimal. And I said, hey, if you just let me write unit tests, just let me test to make sure that the code is actually working correctly before we run the computation. Now we only have to run the computation once or twice. Now all of the errors that we get are physical errors, and that's important. So what I'm saying is by following appropriate software development practices, you can make the code a lot cleaner, and that's important here. That doesn't sound like a healthy dev cycle. No, it wasn't a healthy dev cycle, but I couldn't do anything because I was kind of limited in what I was allowed to do at the time. Also, if you don't have a good enough GPU for your simulations computation and have extra money, you can rent GPUs here. Oh yeah, you can also do it via the Amazon cloud. So the EC2 Amazon services allow for GPU computation. Almost every modern supercomputer nowadays will have some GPUs available for GPU computation, because again, it is the next area. It's where people are going in the field. It's very important that people know about the area. So this is, I guess you could say, the next area for computation. However, there are areas in the future, like for example, cognitive computing and quantum computing are both areas that people will eventually move into, but massively parallel computing is where we're at now. One more thing I want to point out is that there is another device called the FPGA, which is a field programmable gate array. This is another area that people are pushing into currently, and it is a big area of modern, I guess you could say, research and development. One thing to note about FPGAs is that they are actually like programmable hardware. So the idea here is that if you have, like, for example, a sparse matrix or something that you can put into, I guess you could say, a classical circuit, by using the field programmable gate array, you're able to get an incredible performance, like way faster than the GPU on the FPGA. However, this matters. It matters if you can actually write your code such that it can run on the FPGA. Same with this. If you can write your code from the CPU to GPU, do it. If you can write the code from the GPU to FPGA, do it. But most of the time, it's very, very difficult to write the GPU code, and it's very, very difficult to write the FPGA code. So oftentimes you're still stuck with CPU. In fact, a lot of times you're still stuck with massively parallel CPU code. And now I want to talk about why exactly. Because there are limitations to using the GPU, and this is something that I think a lot of people, when they first hear about GPU computing, they think to themselves, oh wow, this is it, this is going to replace all of my computation. But that's not the case. The CPUs are still very important for a number of different reasons. And again, like I just said, no matter what area of computation we move into, I would be very hesitant to say that the next computer will not have a CPU. However, it may have additional cards. It may have an FPGA slot. It may have a GPU slot. It may have a QPU slot for the quantum processing unit, or a CogCU slot for the cognitive processing unit. Like, there may be different slots in your computer to fit in these different devices. But for the most part, the CPU is still the unit of computation that we need. Like it's the most important part of the computer for modern programming. While we're on the subject, if you need AI computation, oh yeah, the TPU. No, I don't know much about the TPU. I'm gonna be honest. It's something that I don't know about. All I know about is like the true north stuff with IBM. So a little bit of cognitive computing there. But TPU is a bit different. Replace GPU for brains and link them together. Man, actually, you're joking here, but literally all machine learning is done on GPUs nowadays. So we're getting to the point where potentially, yeah, you could replace some brain with the GPU, but we're not there yet. Okay, so let's talk about GPU. In particular, I want to talk about GPU limitations. Okay, so the first major limitation, the limitation that you're always going to hit with a GPU is memory. GPU memory is limited, and this is something everyone knows about. This doesn't matter for games. Rather, it doesn't matter if you're buying a GPU for games. It does matter if you're developing games. The memory limitation on GPUs is at most probably going to be 12 gigabytes of, we'll say gigabytes, GB, that's what I'll do. 12 gigabytes of memory. This is nothing, literally nothing. I mean, for the most part, when you're doing computation on the CPU, you'll need like 128 gigabytes of memory, you know, to do your system, if you're using a large memory system. So then it's like, well, if we only have 12 gigabytes of memory, what can we actually do on the GPU? That's the question. And the answer is you can still do a lot, but you have to play with your memory a lot. So this means that because we only have 12 gigabytes of memory, you're gonna have to do some computational tricks in order to just figure out, like in order to, how do I put this? Kind of manipulate the memory you do have available. Now, in some cases, 12 gigabytes is actually more than you'll need. If you're doing some physical simulations, you can kind of get away with such a large or such a small amount of memory. But if you're doing, for example, genome processing, that's impossible to do on a GPU just because it requires way too much memory. Hey CSK, I'm doing okay. Thanks for asking. How are you, man? We can blame GPU for poor performance. I mean, not usually. Usually the CPU you can blame for poor performance. There we go. I can say it. But the GPU can be blamed for having a low amount of memory. Development time is also another sticky point. So dev time, I'll just put down here. It just takes a while. I'd say maybe 5 times as much dev time. Something like maybe 5 to 10 times, honestly, as much dev time. Like for example, the project that I'm working on now, I could have written the CPU code in literally an afternoon. But I can honestly tell you that I have no physical way of writing my GPU code faster than I did. My GPU code took 2 years. Meanwhile, my CPU code, if I were to write the same thing on the CPU, I could literally do it in an afternoon without too much trouble. Why does GPU have such a low amount of memory? I mean, the problem is that the GPU is obviously a hardware device, right? So the memory limitations are basically based on what the manufacturer can embed into the device itself. So where on the CPU you have extra slots to put in your RAM, on the GPU, the RAM is inbuilt into the GPU itself. So you have a small amount of memory to work with there because you have to fit it all on the same card. Yep, this is also important to note, but I was going to talk about, we'll talk about that now. So as Cobalt said, copying memory from the CPU or GPU back and forth, that is actually the slowest process of your computation. So the next memory, I guess, or the next limitation of the GPU is I guess that you have to do it blind. So this means, by this I mean, I guess I'm going to say lack of debugging, we'll say. Debugging. So the problem is your debuggers, like GDB, or in this case, CUDA GDB, or whatever you want to use, these are all CPU based in a way. You have to manually implement all of your stuff, all this implementation, like you have to say, hey, GDB, run this, or hey, you know, my debugger, Nsight, whatever you're using, run this command, right? So when you're inputting these commands, they have to go through the CPU before hitting the GPU, right? And the problem is the transfer of data between the GPU and CPU is the slowest part of your computation. By far, it is the slowest part. So if you're going to do debugging or something like this, you actually have to do this super weird thing where all of your data is on the GPU, which you can't see because you don't have access to it. But you need to do debugging on that data, so you have to do some very weird, just quirky things in order to do this debugging. So what I mean is that, yes, GPU computation has some debugging tools, but these are way, way inferior to the debugging tools that you're used to from CPU computation. So keep that in mind. Dev time is up. It's harder to write code. It's just a pain in the butt. And we'll talk about this lack of debugging actually in a second when we do OpenCL stuff, if we get to that today. Because the OpenCL stuff really, really highlights how bad debugging and like error management and stuff is on the GPU. The final note is, this is not the CPU. So I guess the final note here, where the GPU computation is just hard to deal with, if you compile code for one GPU, it's not guaranteed to work for other GPUs. And that's the problem. Like, for example, if I compile code for my Titan X, it's not going to necessarily work on my V100. And this is a very important thing to keep in mind. You have to make sure that the code is working on each individual card that you work with, because the computational landscape is different for each individual card. And that's important to keep in mind. One of the major problems I had, I spent literally months trying to get my code working on our local supercomputer when it was working just fine on my machine. But for some reason, when I moved it to the supercomputer, this didn't work. I couldn't figure out why, and it ended up being some weird library issues, or it ended up being some weird difference between the hardware and all that kind of stuff. It's just hard. Assembly. Okay, so let's see. What did I miss in chat over here? Let's see. You can always combine more GPUs. Yes, you can. However, Backsays, even if you combine more GPUs, let's say you have 2 GPUs here, the transfer between GPU to GPU requires a transfer to the CPU and then to the GPU, with the exception of NVLink technology, where it directly connects to 2 GPUs. This is new as of the Pascal architecture, so last year, and it's not something that people can do normally. So if you're going to transfer between 2 GPUs, that's kind of maybe better than transferring between the GPU and CPU, but ultimately it's still incredibly slow, and you don't want to do that. If you can, keep all your computation on a single card. If you can't, hopefully, may God have mercy on your soul. That's kind of where you're at here. What do we have here? Where are we? But couldn't you just make bigger cards for scientific computation? I mean, there has to be a limit. Yeah, so this is also another good point. AMD in particular are really trying to increase the amount of memory available on a single card. So they have the ability to basically put 100 gigabytes on a single AMD card. Problem being that it's AMD, and no one uses AMD for scientific computation because CUDA doesn't really work very well on AMD cards. You have to use OpenCL, which is much, much harder to develop for, and like I said, development time even of CUDA, which is straightforward, is much higher than development of just CPU or Fortran code, and we're talking about scientists here. Scientists aren't necessarily programmers, right? So if you want a scientist to write code, you're gonna have to make it easy for them, which is why CUDA is still kind of king, as much as I hate to say it. Let's see. What do we have here? Again, quadro cards. Yeah, it's kind of a newer thing, but people are moving there. But even then, it's double the RAM. Yeah, which is fine. Double the RAM is still great. Don't get me wrong, we're totally getting there. But the current state of the art, I think, are V100s. But let me check something. V100s are the Volta 100 series. So let me check V100 memory. What do we have here? It's probably going to do the stupid thing it always does. Let's see. I just want to know the amount of memory available. Let's see. Teraflops. I don't care. Oh, nice double precision, but I don't care. What I want is memory. 32 gigabytes. Yep. So that's the current. That's what people can currently do. This is the highest performing card I have access to. 32 gigabytes, which again is still fine, but it's not quite what we want. Let's see. What do we have here? 5K. Where are we? Double the RAM. They're bigger GPUs. Yep, this is true. I say usually 12 gigabytes because that's the Titan X. I usually just assume I have 12 gigabytes, but you're right. This is incorrect. 36. What's it? 36? I think is the number that we just looked at. Oh, 32. Shoot. So 32 gigabytes looks like the largest amount of memory available. What do we have here? In general, it's even faster than CPU memory, and it's because it's fast, it's expensive. Yeah, this is also true. The speed in the memory is different. What do we have? They're bigger GPUs. You're correct. You're correct. I'm sorry. I said 12 gigabytes because that's what I have access to on my modern on my development machine, but honestly, there is more than that. GPUs are expensive because crypto mining, like 90% of it is that. Yeah, everything does GPU computing there. Did I miss something? Okay, I totally missed something. Oh, adding Euclidean algorithm in x86 assembly. Oh, nice. New language in... I feel like I'm missing something here. Anyway, it doesn't matter. Point is, if you use console.write as debugging. Yeah, we can do that for debugging. That's true. Happy birthday. Whose birthday is it? I totally missed this. Phil's birthday, man. Okay, whose birthday is it? It's not my birthday. No matter who's saying it's my birthday, it's not my birthday. I'm sorry, I missed that. I'm like way behind. Just messing with him. Yeah, so this guy apparently knows that your fan apparently knows that I don't like celebrating my birthday, so that's nice. Let's see, what do we have here? Just messing with system access from where? 32 gigabytes, you can install Linux on it. 36? You can probably. Okay. I think it's definitely not my birthday. They didn't. Oh, by the way, that's your fan. Thank you so much for the subscription, man. Really appreciate it. As I said before, really appreciate all of the support from all of you guys. You guys are like an amazing community. Like I seriously appreciate it all. I like the fact that we have x86 assembly too. It is your birthday. No, it's not my birthday. I don't want this to be a recurring thing. Like I actually get kind of a little bit miffed when people talk about my birthday. It's just one of those things. I don't deserve it. Like, no one deserves a birthday. It's kind of a waste of time. They didn't do anything for it. Like, it makes no sense whatsoever. You're just all of a sudden it's like, oh, great, you lived another year. Pfft, who cares? Like, it's just kind of a waste of time. I don't really like people celebrating things about me. It's kind of just weird and awkward, and especially when I don't deserve it, you know? Like, maybe it's okay, like, if you publish a paper or something that gets a large impact factor or something, fine. I understand maybe celebrating something like this or doing something amazing. I understand celebrations here. But I don't understand celebrating birthdays. It's like, why? Now leave. Let's see, what do we have here? Now leave and never show up until after resubbing to please my bank account. Oh, no. Please, don't do that. Like, just, I appreciate it. I really do appreciate it. But don't bend over backwards for this. I don't know, ASM? I don't know what ASM means. I just wrote it to learn. Let's see. Give me a reason to stuff myself. Maybe. You sound so depressed when you said that. I just get really down when people celebrate my birthday. I don't know why. Like, I just get really sad. It's just one of those things, you know? Do we have anyone that knows assembly? I think we have maybe one person that knows assembly. I don't know. Oh, assembly. Yeah, probably. I'll stop messing with you. No, don't worry about it, man. I mean, it's fine. I just wanted to get that out in the open. So, for now, no, don't worry about it. That's your fan. I'm a fan. It's cool. Okay, so I think these are the major limitations on GPU computing. There are a few more limitations here and there, which we'll talk about as we get to it. The main problem is the following. So the main thing about development is that because the GPU does everything in parallel, we have to talk about parallelization. Okay, so we're moving back to the GPU computation stuff. I think I caught up with chat. Have you ever considered that celebrating the birthday is for the mother? Yeah, maybe, but it's not done that way. And also, I don't live with my mom anymore, right? So when I was in the house, I always celebrated my birthday. But now that I'm out of the house and I can live by my own rules, I want to kind of move away from that, you know? And that's what I said. It's like, hey, I'm no longer like living with you guys. So kind of let me do my own thing. And my own thing is, don't celebrate my birthday. You know, like I was arguing that for years, like ever since I was like 12. I remember I sat down with my mom and I was like, look, I don't want to celebrate my birthday this year. And then she was like, I don't think that's okay. And I'm like, okay, fine. So when I leave, when I'm 18, I'm not going to celebrate my birthday anymore. And like, I remember like one of the motivations I had to move out was so I didn't have to celebrate my birthday. Like that was like one of my major motivations. Like I was like, yeah, I no longer have to celebrate my birthday. Boom, this is amazing. So that was like one of the main reasons. Like it's just one of those things. Anyway, sorry. I know this is super rambly. I'd love to see James look at ASM code. No, thank you. Programming part of the doodling xernal part. This is the programming. Well, okay, we're at the doodling xernal part. We're gonna get back to the we're gonna get to the programming in just a bit. So for parallelization, here's the thing that's important. The way the GPU works is that we have one large unit of computation known as the grid. Okay, so for example, if we have a huge, let's say, block here, this is called the grid. I shouldn't have said that notation. This is the grid. Basically, we take our simulation data and we project it onto this grid. Okay? Then, on top of that, we split these up into blocks. Okay? So the blocks would be very large units of computation on top of the grid. Okay? And then on top of these blocks, we then split it up into threads. Okay? So each thread would be something like this in here, if that makes sense. And the reason we do this is to kind of get around the fact that we have a limited number of CUDA cores available. That is to say, oh, by the way, Ongoris, thank you so much for following, man. I totally missed that a few minutes ago. So we have grids, blocks, and threads. So the grid is a large unit of computation. Block is slightly smaller. Threads are slightly smaller. Because we only have a small amount of CUDA cores, basically every thread, this is going to be related to a core, right? So this means that each thread is an individual core that we're working with here. However, because we have a limited number of cores, we have to split the grid into individual blocks that allow for us to basically do units of computation batched in a way. So we do this in parallel, this in parallel, this in parallel, this in parallel, or we do these blocks in parallel, these blocks in parallel, these blocks in parallel, whatever. Basically, we just put the computation up, we queue the computation up into each individual core, and it's all scheduled according to how we've written the code, if that makes sense. So in terms of the notation that we'll be using here, grid, blocks, and threads, that's kind of the idea. And then from then on, it's just a matter of basically writing your code in such a way that it can be optimized for the GPU, right? So let's see, what do we have here? As a note for OpenCL, these are called work items, these are called work groups, and this is called, I don't remember off the top of my head, but it's called something else. They're called different things for OpenCL, but for the most part, it's fine. What do we have? I have a question in here. Let's see. I don't really celebrate my birthday at all. Nice. It'd be funny if your parents celebrated this birthday. How do you think of research project ideas? As a note for research project ideas, they all grow organically from previous research ideas. So for example, if you're working on some physical simulation, you realize, hey, we need like 5 or so algorithms to get the simulation working. So let's go ahead and do the research into these algorithms so that we can do the research project that we have at hand. And then after that, you're like, well, wouldn't it be cool if we did this instead? Wouldn't it be cool if we do this instead? So basically by doing one research project, you gain basically insight into the field such that then you can move on to further research projects. That's what I would say. And that's kind of how you do it. So I understood you right. We should all send you a birthday card. Please do not. What do we have here? If you want to see some dude talking about ASM, maybe watch Chandra Kareth on YouTube. Oh, yeah. I should probably look into this. Let's see. I'm running my first game in assembly. Nice, but that seems like a lot of work. YSM, because I want to write the game in C64. It's just the 6502 is a nice starting point. ARM is also nice because ARM... Okay, let's see. I get confused because there's a big turbo assembler in C64. What if you have a matrix that requires computation that's bigger than your GPU count? Do you just do a second computation with the remaining data? Yes, that's kind of what you do. So like I said, you do it in batch. So you'll do one core, one block, another block, and you do these blocks in parallel. So basically what ends up happening, and this is an important point for one of the problem sets that I gave before, like each individual core will say this is core 1, this is core 2, core 3. They kind of have bits of data that they'll have to be dealing with, right? So we give core 1, piece 1, piece 2, piece 3, piece 4, piece 5, piece 6. That's kind of what we do here. And so the idea is then we have computation number 1 and computation number 4 queued in core 1. And we have computation number 2 and 5 queued in core 2. Computation 3 and 6 queued in core 3. This isn't very present in CUDA, but it is very present in OpenCL. And this is actually one reason why I do like programming a bit in OpenCL, because it's clearer what you're doing with the hardware. But that said, again, OpenCL is a pain in the butt for a number of other reasons, so I don't use it for my research code, if that makes sense. What else did I miss? Let's see. Is this tutorial on CUDA? I guess today will be on CUDA, but if you guys are interested, I can do another day on OpenCL, maybe on Monday. What if you don't have previous research ideas? Honestly, Greenie, if you don't have previous research ideas, then talk to someone. I started research as a physicist at Auburn, and I knew what I wanted to do. some sort of heavy computational project. So I looked around for a heavy computational project, found said project, learned a lot in the process, and then slowly but surely my methodology, my ideology, my way of doing research changed into the area that I'm in today. And that's kind of the idea. Because CUDA is NVIDIA and OpenCL is AMD, all right? That's not exactly true. So CUDA is specifically NVIDIA, that's true. So CUDA is an NVIDIA-based programming language. However, OpenCL can run on either NVIDIA or AMD cards. So if you wanted to write something that works on all cards, you need to write OpenCL. But if you want to write something that only works, but if you want to write something that's used on an HPC, for the most part, the HPCs will use NVIDIA, so you can get away with using CUDA. That's kind of the idea here. I know there's a CC65 compiler, and I've never written assembly before. I'm missing some stuff. I've never done a single research project. Let's see. I mean, you'd have to talk to a professor or something. By the way, Gathros, you should use assembler if you don't have access to Stack yet at boot up. Let's see, because CUDA as NVIDIA, since I got an AMD card on my MacBook, OpenCL would be quite nice. Yep, so you'll have to use OpenCL for that. In addition, OpenCL can be used on the CPU, but if you're going to use it on the CPU, you're going to have to like emulate a GPU or something like that if you want to do the GPU part of the OpenCL stuff, if that makes sense. But OpenCL actually is a bit different than CUDA. So OpenCL is like this open compute language. So it's meant to kind of be able to do computation on everything. So CPU, GPU, FPGA, it's all technically possible with OpenCL, whereas CUDA is specifically for graphics processing units. Because let's see. If I missed anything, please just repeat it. We're getting a lot of comments, so I'm trying to make sure I'm caught up with everything. So just let me know. Okay, so for now, we're gonna move right into the CUDA code. If you have any questions, comments, concerns at this point, please let me know, and we'll go into that CUDA code right now. I've got a feeling that the CUDA code will take a bit of time to write, so I think maybe a good place to stop today would be ending with the CUDA computation. However, I do feel like we can come back another day and do the OpenCL computation, or even have maybe a day a week that we talk specifically about methods in GPU computing, or something like that. I'd be totally into that, because I don't know, I find GPU computing super fascinating. Massive parallelization is my jam. Like, I really like it. But this is your call, so it's up to you guys what you want to do. Short intro to OpenCL. So again, I think today we'll probably end with CUDA, and then yeah, OpenCL next time. So maybe we do like a GPU day every week, like I don't know what day. Like maybe every Friday we just take a step back and we do GPU stuff, or something like this. Don't get me wrong, JSPP, I agree with you. I don't like the fact that CUDA is so closed and associated with NVIDIA. It's just a pain. But it is what it is, you know, like, it's still the king of GPU computing, specifically because that's what everyone's using, you know? So it's an unfortunate case, but it's better than MATLAB, at least. CUDA today, OpenCL next time. Yeah, that seems fine. My friend does electrical engineering, and I help out a lot with his projects. So fun. Yeah. I also like open stuff more. Okay, good. So let's go ahead and move on to the CUDA code. So I'm going to CD into project, and I'm just going to put it in Simuleos ls. Let's just go ahead and create a directory here. Make directory GPU. Actually, maybe we already have a GPU directory. CUDA. We probably have a CUDA directory, right? Yes, CD CUDA. What do we have here? So I think what I'm going to do. What was I calling these things? Okay, let's go and do make directory, and we're going to do GPU, because this will probably, GPUE, why did I do that? Remove directory, GPUE, that's my code base, so every time I try to write GPU, I write GPUE, CD onto the GPU. Okay, quick ls here. There's absolutely nothing there, because I just got there. Hey, Zartuo, what's up? CD projects, Simuleos, and GPU over here. So for the most part, I'll be doing the thing I normally do, where this side over here is computation, and this side over here is going to be for coding. What is the point when you need GPU computing? Is it faster at a certain point? Yeah, it's much faster at a certain point. So like I said before, here is our code base, for example. Our code base is a completely GPU-based code base. GPUE is the name of our code base. Here's Trotter Suzuki GPU, Trotter Suzuki CPU, and GPE Lab. So this is in log scale. Our code takes about 10 seconds to run, as does the other code in the area for GPU computing. They're roughly the same, but it's 5 times faster than the fastest CPU code. This is well-optimized CPU code, and it's literally 200 times faster than well-optimized MATLAB code. So as far as when it's worth it to do GPU computing, it's basically worth it whenever you can massively parallelize your system. And again, we just talked about this. So, yeah, also having way less memory to work with does make you way less lazy about optimizations. This is true for the GPU as well, although I understand that you guys are probably talking about ASM stuff. But it is true, like if you have very little memory to work with, as you do on the GPU, again, a lot of times if you're just using a consumer card, you have like 2 to 4 gigabytes. This doesn't really apply if you use modern co-processors though. What do you mean? It does still apply. Okay, so I'm actually going to ask you, Zartio, what you mean here, because this guy right here is, this is done, in a massively parallel way. Like, let me see what they're working with here. CPU. So they don't, let me see what they tell us. CPU kernels ran 4-core. So to be fair, this was just done with a 4-core, i7. So that wasn't very well optimized. But no matter what you do, you will not be able to match GPU performance on a CPU if we're talking about if we're talking about something else. Oh, microcontrollers are slightly different, yeah. Let me see. Maybe I'm misunderstanding. So co-processing is like, it's a Fortran term, so I might be misunderstanding what you were talking about. What do we have here? Xeon Phis have 72 cores with 288 threads. Correct. But Xeon Phis died. Like, they are dead. So, like, you can tell us, you can say that Xeon Phis... Okay, you're right. Xeon Phis could, in principle, compete with GPUs. But practice-wise, they didn't. Xeon Phis had their time to shine, and they just blew up, you know? Nowadays, they're not being developed anymore. And so, yeah, you can develop a massively parallel CPU device, but the massively parallel CPU device also has a heck of a lot of challenges writing code for it, and ends up being still harder to write code for than the GPU. And the GPU is still just as fast, if not faster, in most cases. So, like, if you're going to write a massively parallel CPU device, you can, don't worry about it. But it's been experimentally shown that it doesn't work. I mean, at least not in practice. Let's see, what do we have here? Kalu, Phantom, thank you guys so much for following, man. I just realized that and I missed it. Okay. So, again, I'm not very little of a GPU. Oh, I see what you're saying. I misunderstood. I thought you were arguing that there was something... Yeah, okay. I agree. 1080 Ti is 20 times more threads than Xeon Phi. Yeah, but the Xeon Phi has the explicit, I guess you could say, advantage that it's using CPU cores, which means you can basically write your regular C++ code and it will work almost immediately with... Okay, there's a lot of optimizations, but it can work on the Xeon Phi, where it definitely will not work on the GPU. Meanwhile, the Xeon Phi cores are also stronger, so for certain levels of parallelism, you could actually want the Xeon Phi over the GPU. For some reason, Intel killed their dedicated GPU card. Yeah, this is something I realized recently, and I'm not exactly sure what's going on there. And hook up a human brain to a computer and use the brain to compute data. This is actually a thing. Okay, let me talk about that too, just since we're rambling for just a brief minute. Just let me be Rambleaos for a bit. What is it? It is quantum moves. So there are optimization problems that we have in physics all the time, right? And these optimization problems are solved via optimal control methods and stuff like that. So sometimes, or what these researchers decided to do was they said, look, if we're going to create a machine learning algorithm to solve our physics for us, let's just gamify it and have a whole bunch of people solve our physics for us. So that's actually what they did. They created a game that would allow people to basically move a trap and move the wave function in the trap, and then now it's a game that people play, and it was actually used. Their results from the game were actually used in research. And this is kind of cool. It's like, hey, it's like turning everything on its head. Instead of using machine learning to solve something, we use actual human brains to solve the problem. So it's not quite hooking, hooking yourself up to a GPU, but it's interesting for understanding, maybe. I'm missing a couple of these guys. What do we have here? Oh. Oh, man. Okay, so let's go ahead and get started. So what we're going to be doing, the system we're going to be working with today, is going to be for like the hello world of GPU computing, what's called vector addition. So vector addition is basically, it's super simple, right? So the idea is, let's do new page before. We have two vectors, A and B, and we're adding them into vector C. That's all we're doing. So we'll say, I have to go. All right, cool, well, see you around. This VOD will be up if you want to take a look at the rest of it. And also I'll put it on YouTube probably on Monday. So we have vector A here. Let's say A. We have vector B here. And finally we have vector C here. And the idea is we add A and B to get C. That's the entire thing that we're doing today. Super straightforward, isn't very complicated. That's what we're doing. So let's go ahead and do it. So what I'm going to do is I'm going to write code such that we can do it easily on the CPU. Now, for the record, I'm going to be using notation that is reminiscent of C, not C++, because CUDA uses notation that's reminiscent of C and not C++. So it's going to be a little bit weirder than regular C++ code. So I'm just letting you guys know that at the start. The code itself is going to be very archaic, and again, that's because the code that you write for CUDA is also archaic. So what I'm going to do is I'm actually going to pop over here. So my side screen, I'm not going to have the notifications up. I'm going to put the code on the side screen just to make sure that I'm not doing anything dumb, because I don't want to accidentally, do something that that I will regret later in life. Okay, nice. Okay, so let's go ahead and go. How can any language be weirder than C++? This is going to be C. The hello world of GPUs is the rainbow triangle. What? Okay, let's go ahead and go into, I guess I'm just going to say vector addition .cu. Okay, so CU stands for CUDA. This will be specifically for CUDA code. So obviously we start like we always do, include IOStream. And for the record, let's just also include math.h, because I'm pretty sure we'll need it for something. Int main. And here we have our standard, we're starting up our CPU, right? This is how we normally write code. There shouldn't be any problems with this. Okay, so what I'm going to do is I'm going to create a few double star arrays. And actually, what I should probably do is call them floats, because again, GPUs are better designed to deal with a single precision instead of double precision, especially for I guess you could say consumer hardware, but hey, let's presume that we're on an HPC where we have infinite access to, we'll say, double precision cards. So fine, we'll use double precision here. So we'll do double star A, and of course star B, and star C. Okay, so now we have our three guys in here. And again, using C code, because this is more standard for CUDA code. So just bear with me. You guys are going to hate the way that I'm writing this, but this is a way to do it. So what we want to do is first malloc everything. So we're going to say A is equal to double star. Let's do quickly here, malloc. And it's going to be size of double times n, okay? And again, I'm doing this in a very particular way to remind you guys how this is done. And I'm also going to do int n, and we're just going to set this equal to, let's say, 1024. Nothing very complicated. That's what we have. Okay, now we're going to have b is going to be equal to the same thing, so let's just go ahead and dd here, and let's just do a quick yank, paste, and do b and c. Now I forgot a semicolon on the end here, so let's go ahead and add those guys in here. 1 second. Oh, come on, dog. What am I doing with my life? Ah, come on. There we go. Ah, dang it. You. Why? Yes, that's what I wanted. And of course, we're going to have to free 1 second. A and B and C. Okay, so now we'll just go ahead and initialize A and B. So I'm just going to say initializing A and B. For int I, we could do size t. I less than 1024, so we'll say n plus plus I, pop this down here, and then we're just going to say, what should we initialize these guys to? It doesn't really matter, right? So we could do, I don't know, let's just set all A and B equal to 1. Okay, just something straightforward, nothing crazy. So we'll say A of I is going to be equal to 1, and B of I is going to be equal to 1 as well. No, note, I'm not initializing C, but I can initialize C. Let's go ahead and do that too. Yank paste here, let's just go ahead and do C is going to be equal to 0. Okay. Now, to do the vector addition, it should be done in the following way. So here is the actual vector addition. Addition. And we're just going to say for, just another for loop. I'm doing this outside for an explicit reason that I'll talk about in a second. I equals 0, I less than n, plus plus I. And we're just going to say C is going to be equal to A of I plus B of I. Okay. And then down here, we're just going to do a quick check just to make sure it works. And so here's our check. Okay. Oh, come on, dog. Let's just do another for loop here. Size t. I equals 0. I'll catch up in chat in just a second. Sorry about that. I less than n. And then we'll do plus plus I, pop down here. And for our check, I guess we'll just say, I mean, we can assert that, we'll just do this. If C of I is not equal to A of I plus B of I, fair enough, then we're just going to do just some sort of print out. So std, C out, yo, you failed. What a loser. Ha. New line. And then we'll just say exit 1. Nice. Okay, that's our code. Let's see, what did I miss in chat here? Fortune code for the algorithm archive. Oh yeah, I'm looking forward. Looking forward to reviewing that soon. I have a lot of other stuff to get there. GPU crashes and shows an embarrassing image. I don't think it can, actually. Emoji code is probably clearer than C++ standards. Funny fact about C structs is you can save memory by changing the order the items instruct. Actually, how does that work? Yeah, let's see. Yeah, struct. Oh, okay, yeah, I could see how that could happen. Yep, that's fair. That makes sense. Let's see, plus you need csc lib. Nice. Okay, so I don't think I missed too much here. So let's just go ahead and go over here. To compile this code, let's just do nvcc vecadd.cu. I forgot a semicolon. 28. Where is that? I failed. nvcc creates a.out. Oh, I forgot to output anything. I guess we'll say you passed. You passed the test. Congratulations. Nice. Okay. New line. Congratulations, you test the pass. Dude. Why can't I speak today? Okay, doesn't matter. We got it. So again, this is one way in which we could do CPU-based computation. It's rather straightforward, and would be what you would expect for things to be done on the CPU. It's just super straightforward. A note here is that we have this for loop in here doing the computation. That is to say that we go through each individual unit of our matrices, of our vectors, and we add them together, right? So we have to go unit by unit. And this for loop is very important. I wrote it this way for a reason. We do have to do the initialization still on the CPU, or rather we have to do the initialization still at some point. But for the most part, the computation on a CPU is usually done with some sort of for loop or something like that. Hard's a word. Use calloc, not malloc, and for loop. This is fine. What we have here is fine. Because I'm using malloc for an explicit reason. So the first struct in memory is A times BBB. Yeah. This is about the C stuff. Okay. So let's go ahead and move from here. So now we're going to move into the actual CUDA code here. So we have an option. Should we write the CUDA function first? Just raise of hands here. CUDA function first? Or fixing up the main function first? I think... Okay, I know I asked for a raise of hands, as in I wanted your guys' opinion. But I think what we're going to do... again, Gathros, I used malloc for a specific reason, which I'll talk about right now. I vote for C, but you can't see our hands. Exactly. So I'm going to assume you guys said, let's write the GPU kernel first. Yeah, nice. Okay, so now let's go ahead and write our first GPU function. And this is where things get a little rough. What do we have here? Gem? Wait, what is this? Oh, okay. Here's where things get a little rough. Okay, so let me go ahead and get a quick sip of water. Okay, so what I'm going to write now is going to be this for loop right here on the GPU. Okay, so let's go ahead and do that. We start by doing this global void vec add, and we're just going to read in double star A, double star B, and double star C. Okay, so a couple notes here. First is that we're reading this guy right here is called a global. There's three potential, I guess you could say, function types that we can create in CUDA. There's global, there's host, and then there's device, okay? So for CUDA computation, host is our CPU, device is our GPU, and global is something that can be called from either the host or the device. And that's important. Husky, sorry for James not noticing here. Oh, dude, Husky, did I miss you? I'm sorry about that. Hey, thanks for coming in. I'm so sorry. We're not doing HTML today. My bad. I'm so sorry. Thanks for picking that out, Gathros. I can now see your name all the time, so it's nice. Okay, so again, global means that it can be called from either the host, which is your CPU, or the device, which is your GPU. If you want something that can be done specifically on the device, you call it device. If you want something that can be written, can be called specifically on the host, you call host. Now, here's the tricky part. Global is not the same as doing this. So I could say that this function is callable both from the host and the device, but global isn't quite the same. There's a very small difference, I guess you could say, and that is that for global kernels, they always have to return void. So this means that when you're doing GPU computation and you're calling global kernels, you're going to have to return void. But with with device and host, you can obviously return doubles. So if you wanted to return double star onto a GPU function, you would have to call it a device function. However, this is going to get complicated later on. This is kind of why I'm noticing it now. Oh, we have a raid. Dude, oh bother, thanks so much for that. Let me go ahead and check what we have over here for notifications. Oh dude, yeah, thanks so much for the raid party of 17. Like again, this is another situation where like, really appreciate it, man. Thanks for coming in. Let's see, what do we have here? Twisted Sister, thank you so much for following, man. Really appreciate it. No algorithm today. Laos is is doing an introduction to GPU computing. You can apparently check related stuff out here. Oh, yeah, that's true. You totally can. So that's what we're working on today. Just a general introduction to CUDA, basically, is what we're doing. We've got another maybe 40 minutes left in stream. Yo, oh bother, how was your stream? I hope it was okay. Feel free to talk about it here. If you guys don't know, if you've been on my channel before, Obother is a wonderful channel. Like, he's just a great guy. You should totally check out his stuff if you can. Big fan. Big fan. Okay, so let's get back to the CUDA code. And of course, if you guys have questions, please ask. Okay, so as far as this global global function is concerned, it does have to return void. So now we're going to get into the tricky part. We need to find our global thread ID, okay? And this is the notation we're going to use. Int ID is going to be equal to block idx dot x times block dim.x plus, you're going to hate this, thread idx.x here. What I'm going to do is I'm going to finish writing the kernel, and then I'll come back to this. So now we have another thing, check to make sure we are in range. So if ID is less than n, which I guess we'll be reading in. So let's go ahead and read that in. Then we do the following. Okay. C of ID is going to be equal to A of ID plus B of ID. Okay, so let's start with the simple stuff. Down here, we don't have a for loop. For loop is gone because we're doing GPU computation. It's all done in parallel. So this guy right here is the same as this guy down here, right? Now, let's talk about how it does it in parallel because this is actually rather confusing. We absolutely failed to install Afterburner Kit into a GPA. GBA, nice. And what GPUs am I asked? Click here. Oh, nice. Dude, you're doing like awesome. Good job, JSPP. Really appreciate it. Cool. Okay, so let's pop down here and let's talk about exactly what this other notation means. Because like I said, this is a computation. So basically we're trying to find some unique thread ID on the GPU that we'll be adding A and B together with. Does that make sense? Like we find some thread in A, some thread in B, some thread in C, add A and B to get it. I will tell you about Calloc in just a second. Gathros, give me a second. Like, just give me a second. Like, I understand that Calloc is better than malloc, but like, malloc is the notation that's used for CUDA. So like, I need to use malloc so that you can, like, it was meant to be like a tie-in. Like, it's like, here's malloc and here's CUDA malloc, which I'll show in just a second. Like, again, we're not there yet. Now let's talk about this int ID because this is actually very complicated and super annoying. So I already did it. Okay, so let's say you have a grid that looks something like this, okay? So here's your grid, and let's just say we have 1, 2, 3, 4, 5, 6. Very, very messed up grid, but this is our grid. If you want to notate this, so you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? If this is how you want to notate things, you're gonna have to do something like this. You're gonna have to say that each index, something like this, let's say. So for I equals, just quick notation here, 0, we'll say to X dimension, and then we say J equals 0 to Y dimension, right? Something like this. Another for loop in here. Then we'll say index is going to be equal to, we're going to say I times X dimension plus J. I'm sorry, this is going to be Y dimension. Okay? So, in order to find each individual index, all you've done is you've taken I times Y dimension plus J, right? This is a standard indexing if you want to take, like, for example, a two-dimensional array and project it down to a 1D array, right? That's kind of the thing. Dude, Gathros, come on! Just chill. Like, it's fine. Like, I need to use malloc because CUDA uses malloc. That's the point. It's an analog. Like, it's not that big of a deal. So we have the index here is going to be I times Y dimension plus J, right? This is a standard indexing, right? So what we're going to do is we're going to pop down here, And we're going to say the following, right? So here's the standard indexing that we have. Like, I don't know. I'm sorry. I didn't mean to blow up, but it's just like, come on. Like, it's not that big of a deal. Anyway, so yeah, no. Again, I to be fair, I'm not actually angry. Like, I'm not angry at all. But it's just like, come on. Like, this has absolutely nothing to do with the topic at hand. So it's just kind of like, bah. No. Jellius Maximus, please. Don't tell people to leave. Like, there's no reason for Gathros to leave. He's fine. It's perfectly fine. Like, everyone has their own opinion. But like, what I'm saying is that like, this notation is crap. What I just wrote, this crappy notation. It's just like it has nothing to do with the topic at hand. So it's just kind of like, you know. I get super angry at MATLAB. Anyway, so that's the point with the indexing. So on the GPU stuff, you notice that we did a very similar index here. We said that the index is going to be equal to block dimension dim.x, and this is going to be the same as the y dimension over here, times block idx.x plus thread. Oh, come on, I can spell thread. idx.x. Okay, so these correspond up here. So this I corresponds to this block idx.x. This y dimension corresponds to this block dimension.x. And the j over here corresponds to thread idx.x. You're right. Just, I mean, it's fine. Again, this is not the reason I'm using malloc for a specific reason. Wait, what do we have here? Oh, dude, thanks, Gathros. Really appreciate it. Okay, so now let's talk about what these guys actually mean in the sense that we're working with here. So rather than doing a 2D array, what we're doing here is we're just messing with a 1D array here, right? So the idea would be, let's say we have 1,000 individual components of this guy. So we'll say this guy is 1,024 long. Okay, and we'll say each block, let's say each block is going to be 100 size. So that means each 100 of these guys, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, these are going to be our blocks. Okay, and note here that the block does extend past the boundary here. That is to say that if we need to do all of the computation, we're going to have more blocks available than we have threads. Does that make sense? Like, we're going to have to pick an extra block so that we can make sure that we do this computation here, but there might be a little bit of wasted space over here, if that makes sense. Right. Now, obviously this can be fixed if we just use a multiple of 2, but that's okay. It's not a big deal. Yo, Evil Taco, what is up? Whoever thinks arrays should start at 1 does not understand how numbers and decimal system works. It doesn't matter that much. Array starting at 1 is okay, it just depends. That's something that gets me a little angry. I mean, to be fair, I guess I'm kind of used to both of them. Like, Fortran starts counting at 1, C++ starts counting, or C starts counting at 0. I agree that 0 is kind of more natural for me, but I don't get particularly angry at it. So in a similar way, we have split up the 1,024 threads into 11 blocks. Does that make sense? So we have 1,024 divided by 100 will give you 10.24, and we round up, so we have 11 blocks, right? Is this okay? So then each block, individual block ID is going to be block IDX. So that's going to be each individual block ID. The block dimension is going to be the, I guess you could say, like, how big each block is. So like, for example, if each block is 100, block dimension will be 100. I guess we'll say, this is hard to notate. We'll say this is going to be equal to j, and this is going to be equal to I, right? So this means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Whatever. Pretend I had 11 there. So the block ID is going to be equal to, like, the i's in here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the thread ID is going to be equal to the individual threads in each block here. So then thread IDX is going to be equal to each individual thread in there. So we'll say that's J in the loop before, right? So like this kind of goes through loop for J, and then this is a loop for I. This is super complicated, like this notation is kind of crappy, but like the loop over all the blocks will be like this. For I equals 0 to block dimension, or block ID? No, block dimension. I guess. It's not quite right. For J equals 0 to thread. No, I guess it's the following. Number of blocks. And then block dimension. Okay, so then we have the index, like we had before. I'm just trying to draw the analog here. It's kind of complicated, but it's not so bad. I'm just kind of overcomplicating it here. But again, the overall idea is quite straightforward. All we're doing is we're taking the system and we're parsing it up in such a way that we can attack each individual block with a large number of threads, right? What do we have here? Whoever thinks arrays start at 1, or in computers, it does to MATLAB somehow. MATLAB's dumb, so it doesn't count. Yeah, fair enough. Yeah, okay. So this is kind of what we're doing here with this, with the kernel. I'm hoping it's kind of clear, but of course, if you have questions, just feel free to ask as we move on to the next stuff. Okay, so now we're going to move on to this stuff, and this upcoming stuff is actually kind of a little bit annoying. So here what we're going to do is we're going to be initializing, one second, host vectors. And for the sake of the argument, we're going to call all the host vectors just A, B, and C. Now we're going to say initializing all the device vectors. Device vectors. Okay, pop down here. And so we're just going to say double star, and I'm just going to call it DA, star DB, and star DC. Okay, so these are going to be our device vectors. Similar to what we had before, we're going to have a malloc command. And again, this is why I was doing the malloc command. It's going to be CUDA, malloc, and then we grab the pointer. So it's going to be, I'm sorry, not the pointer. You know what I mean. So we're going to do DA, and we're just going to do size of double times n here. And we're just going to, oh, one second. X here, yank, paste, paste. And we're going to change that to U because apparently I can't spell. And then we just do DB and DC. Okay. So then we have the CUDA malloc command, and we've basically allocated the space on the GPU. So now we have allocated space on the CPU, and we've allocated space on the GPU, right? They're both allocated. Now what we need to do is basically transfer the data that has been initialized on the CPU to the GPU so we can do the computation. Thanks for merging. Dude, thanks a lot. Really appreciate the help. So now what we're going to do down here is we're going to say the following. CUDA mem copy. And we're just going to copy the two things over. So we're going to do D of A, and the size of double times N, right? And then we do CUDA mem CPY, host to device. Very important that this is a capital T. I get a whole bunch of errors every now and again because I keep forgetting that it's capital T. And then we're going to do the same with B. Okay? I'm going to go ahead and comment this guy out down here. And we're going to call the CUDA kernel instead. So we've done the CUDA mem copy. Now what I need to do is define our ints, our threads, and our grid, right? Oh yeah, hi. Sorry if I missed that. Also, again, I can't get my notifications while I'm looking at my code, so I missed a lot of people's follows here. So I do appreciate that. Koshin X, Aftermindy, Stall1, thank you guys so much for following, man. Really appreciate it. Okay, so let's pop down here and let's keep working on this. What I'm going to do here is I'm going to define the grid and threads as integers. However, this is not the general case. In the general case, these ints and threads are actually dim3 values. That is to say that they have 3 components associated with them, an x, a y, and a z. That's why when we do block dimension.x, there's always a .x up here. It could, in principle, be .y or .z, but for now, we'll just assume that they're integers, and it should work. But I guess to be more clear, we could just do dim3 instead. This is kind of your call. It can read both in there. It's just if we use integers, then we can only use block dimension.x, if that makes sense. We can't use .y and .z. However, in this case, that's okay. So we're going to pop down here, and we're just going to say threads is going to be equal to 100. And then we're just going to do the vector add, as we expect. So, no, the vector add is a bit weird because of how CUDA works. So it's just going to be grid threads. And then we're going to do D of A, D of B, and D of C. Okay? And then afterwards, we're going to copy it back to the CPU, copy back to the host. So copying back. Okay, so the next what we're going to do is do that. So the copy back is just the same as the copy forward. So CUDA mem cpy, and we're just going to copy over. So it should be C, D, C, size of double times n, and then we're just going to do CUDA mem cpy device to host. Okay, and then we just do the check and make sure it all works. Pop over here and just run the next NVCC. There's probably going to be a few errors, too few arguments in function call. That's because I forgot to read in n. Grid is used before the value is set. That's because I didn't actually set the grid value. 1 second. So the grid is going to be like the number of blocks that we have here. So grid is going to be equal to, like we said before, int of the ceiling of the computation here. So it's going to be n over, come on, over. Something like this. And I guess we have to do floating point. So something like this. So the idea is we do the total n, which is the total number of elements that we need computation over. We divide that by 100, right? So we're doing 1024 divided by 100. That will give us 10.24. But that means we need to grab 11 blocks. Does that make sense? Because otherwise we're missing 24 units of computation. Okay? Thanks. Appreciate it. Okay, so now let's pop over here and let's do NVCC. Grid was set but never used. I forgot a semicolon. Okay, if I do a.out, it should work. You passed the test. Congratulations. So this is kind of the hello world of GPU computing for CUDA. Again, it's relatively straightforward, but it's kind of more complicated. What are the main non-graphics based applications of GPU computing? Honestly, yeah, there is no graphics based application for GPU computing. GPU computing is, yeah, AI and neural networks. That's used a lot. Most physics simulations can be parallelized in some way, such that you will be using GPUs to do the computation. So for the most part, like pretty much all standard computation, if it can be parallelized, is moving to GPUs. Like in high performance computing, the area that I basically do most of my work in, it automatically, or most things are moving towards GPU computing because it's just so much faster than CPU computing. But yeah, so again, there's some weird things about this hello world that we have here. For example, this vector add. This guy right here has, a grid and threads. So this is kind of us telling CUDA underneath what the thread dimension is, what the block ID is, all this kind of stuff. So it knows what to do in parallel. So this is kind of us doing this guy down here. So it's initializing the loop, if that makes sense. So this is the thing that allows us to tell the GPU what it is that we're working with. How big is the system we're working on? And that's kind of important. And again, like I said before, these are technically dim3 values. So if we change these to dim3 values, then thread, all we have to do is the following. 1, 1, something like this. And then we go down here and we do, and this should be the same thing. So if we pop over here and we just run nvcc, vector add.cu, no operator matches. 1 second. Wait, actually, what is the problem here? Error, no matching operator for these operands. Oh, this should be threads.x. There we go. Narrowing of int, unsigned int. Okay, fine. Dang it. Then we do a dot out of there, and then it works just fine. So this is the same code. It's just all we did was move it such that the initialization is wait, what was I going to say there? All we did is we changed the initialization from ints to dim3s, but ultimately it's the same thing. Okay, so as far as other stuff is concerned here, CUDA gets super complicated for a number of different reasons. And like I said before, there's actually a good bit of stuff available on this GPU group guy. So if you go to GPU group, you go to, let's do skill pill and problems over here. We actually have a problem set that will help you with a whole bunch of different stuff. So here are the problems available. Again, I went through them just a second ago, but like vector addition in OpenCL, matrix transposition, using QFFT, SOBO filter with FFTs, parallel reduction, this is all kind of here. For the skill pill we went through, we also did an example on, what was it? It was on like filtering, SOBO filtering in particular. So we basically just read in an image, did some SOBO filtering, stuff like that. And again, to finish up the question from yeah here, I do want to point out that the fact of the matter is that almost everything is moving towards GPU computation, like I said before. So if you're going to do machine learning or AI or cryptocurrency mining or anything like that, I mean, the GPU is kind of the next unit of computation you need. You're also the official king of Twitch emotes? Ha! Yeah, that is true. Hip has way too many emotes, but that's great. I mean, I appreciate it. He's such an avid supporter of the Twitch EDU community that I'm a big fan. I really appreciate all of the work that everyone's putting into making the Twitch EDU community something great. So anyway, here's the problem set. If you're interested in looking into it, it's what we used for our class a while ago. So feel free to take a look into it. You guys don't have to. It's just one of those things, you know, if you wanted to look into it. So I guess we should probably decide what we're going to do from here. My idea was initially to go through both CUDA and OpenCL today, but that ended up being a little bit too long. So I think what we'll do is probably go over OpenCL next time. The question is, when is next time? Is next time on Monday? Or is next time next Friday? Do we want to make this a weekly thing where we just talk about GPU computing every week? Or is this not interesting enough for that? That's the thing I need to figure out. I don't know. Is it worth doing every week? That's my question. So let me go ahead and open up a straw poll and ask. Yep. Oh, no. Should we do a GPU computing day regularly? Yes. Weekly. Yes. When other simulations end, or there is a lull in content. No. Or I guess we'll put in a meh option also. Meh. Okay, create poll. And let's just go ahead and send this out. What do we have? Look at the Euclidean ASM code, please, on stream. Yeah, I can take a look. GPU group. Let's do, what am I doing with my life? Over here, your profile. Algorithm archivist. Dude, we have 500 stars? Okay. We have 500 stars. That's super cool. Pull requests. I assume it's the one that was just put in. Oh, nice. Files changed. So far, so good. And yeah, that's about what I expected. It's awful, but it is what it is. I don't know if we have anyone who can actually... I mean, obviously Gustorn can, but I don't know too many other people who can actually do the review here. Because this is crazy. It's not something I could easily do. That is crazy, man. Good job. I'm actually a big fan. That is really cool. But yeah, I'm a super big fan. Like this, honestly, to me, is probably up there with the Fortran punch cards and the calculator one. Like, I'm a fan. Lolo Lalo, thank you so much for coming in, man. Really appreciate it. I always say man, but you could be a woman. I'm sorry. But yeah, this is definitely up there for like some of the coolest code we've gotten in the archive so far, I think. I'm a fan. I did both today. Nice. Dude, I'm a big fan. Good job, man. Good job. What do we have here? Including algorithm bubble sort also. Ha. Oh, that's so cool. What do we have here? Files changed. Yeah, I expected that. It's so crazy. I need to learn it. That's why I need to learn it. I'm a woman. I'm so sorry. Thanks for coming in, woman. But no, I really appreciate it. I'm sorry. I say man, but like I know that's sexist, and I apologize for that. In simulated streams, man is person of any gender. I mean, that is true. Like, I have friends who are girls all the time, and I literally just say, yeah, man, don't know like, I always just say man. I need to stop saying man. I need to be, like, more, like, gender neutral. So, yeah, folks, people? Hello, individual? That's what I should say. Hello, wonderful individual. Thank you so much for coming in. Yes, that's it. Let's take a look. Results. Did anyone actually vote? That's the question. Yes, we actually had votes. Yes, weekly. Who doesn't love cows? I don't know. So someone says we should do it every week. The other says we should do it when there's lulls in other content. So I guess so far the vote is to do it every week, and that's okay. That ASM code is really interesting. I don't get it all, but I'm encouraged to learn the basics. Yeah, same here. I know what you mean. No problem. Thanks, man. Ah, dang it! I did it again. I did it again. Oh well, it happens. Okay, cool. I'm a fan. So I'll let the vote go for a little bit longer, but I think doing it weekly is probably a good thing to do. So this would mean that we just set aside like a day for the next few weeks where we just do GPU computing stuff. So this would mean, do you guys want the algorithm archive never to get finished? Look, it won't ever get finished, but I think having a day doing GPU computing is actually quite good, at least for me, because I do know that in my future career, I'll probably be doing like parallel algorithms and stuff like this pretty much all times. Like this is kind of an area that I could imagine myself going into. So it's worthwhile at least to just get the rust off of the basics and stuff like that. Like today, for example, I kind of, it would have been super helpful to go through things beforehand. Like, for example, the calc stuff and stuff like that. I guess we could have used calc, but again, I was using malloc because CUDA malloc, and I wanted to, like, you know, make things... Yeah, I don't know. It's fine. What exactly would we do there? So now we're down 3 days of the algorithm archive? Wait, what do you mean? So next week, then, we'd come back, and we would do OpenCL next week. Yeah, the weekly merge day, the thing is I don't want to do merging on stream so much, because if we do the merging on stream, that's fine. Also, I'm probably gonna, maybe we should mix this in with like meandering Mondays or something like that. I'm not sure. We'll figure something out, because obviously we'll have 4 days of just working on, and we will always have the 4 days working on algorithms and stuff like that. So I'm not intending to like stop that project, obviously. But I am saying that the GPU computation is cool enough that maybe it warrants having a discussion on the side. 1 second. So that would mean we do maybe OpenCL like OpenCL next time and stuff like that. Monday, Friday, algorithm archive minus 1 day GPUC. Whoa, okay, that notation, I have no idea what this means. Monday, Rambaleos. No, okay, to be fair, I think on Mondays, I don't know, we'll figure it out. Mondays are just kind of more of a relaxed day. I think I'll still get stuff done on Monday. Weekly merge day and meandering Monday is the same day, please? Yeah, of course, but the thing is, I don't know if I want to do a weekly merge day on stream. I think I might want to do that off stream. Okay, we'll see. We'll see how this goes. But for the most part, I'll redo the schedule. There seems to be some interest in doing this somewhat weekly, so that seems okay. For now, I think we've... Okay, for now, this is okay. So this is your hello world for GPU computing, and we can talk about it more next time. Leo's looking at PRs doesn't do too much. Right, the right people need to review and look at PRs for things to move. This is true. Okay, so that's it, I think, for the day, guys. We had a discussion on GPU computing, explaining its strengths and weaknesses. If you guys have any questions, please feel free to ask now. And then, after that, let me know if you have any questions, and we'll go ahead and close stream in about 10 minutes. So right now we're looking for someone to raid at the end of stream. We could do Skylius. She's really cool. It looks like Skylius is probably the best bet here. So let's do Skylius, I think. Unless you guys have someone else you want to host. Maybe, yeah. Unless you guys have someone else you want to host, I think probably Skylius is the best one. So cool. Let me know if you guys have any questions, and if not, we'll just go ahead and start raiding. Thanks, Hip. I really appreciate it. As far as the content is concerned, like, again, the primary content we're creating here is the algorithm archive. Just undoubtedly, that's the coolest thing we have going for us. But again, the GPU computation is something that I know a lot about because it's kind of my area. So I would like to learn more about this area, specifically because it's an important area to move into. So, cool. I love that when decreasing number of educational streamers being online at the same time, the view count of the remaining EDU streamers goes higher and higher. Ah, yeah, this is true. Okay, GSP, the easy algorithms are done. I have to fiddle with the other ones, so the next PRs will need a bit of time. Oh, yeah, please, take your time. Ah, dagnabbit, what am I doing with my life? I wanted to go over here, and I want to type in Discord. So if you haven't already, please, feel free to go to Discord, where we have more information, or we basically have an ongoing conversation about algorithms and stuff like that. I'm not seeing too many questions, so I think I'll go ahead and close stream here. Thank you guys so much for coming in. Have a great day, night, afternoon, morning, evening, whenever time it happens to be your time. And I will see you around next time for the next episode of Simuleos. And that'll be it. So we'll go ahead and host Skylius, and that's a good day. Thanks, guys, and I'll see you next time. Bye, guys.